So continue with deflection problems, and I said for some statically indeterminate cases that match or are covered with loading scenarios in the appendix. So we have this problem 36. The text says determine the reactions, complete shear and force bending moment diagrams, and when deflection formula available, put it in the maximum deflection in the form. And then if there's information available for the cross section, the material, comment if it's if it's magnitude and if it's acceptable. Okay, so we have this continuous, I think it's called continuous beam. So let me undo view and zoom. So the first one here, it shows a beam with 3 supports, one right in the middle, and distributed load. That's the appendix scenario G. No, I'm sorry, not G, but rather H. So just distributed load and 3 supports. We have to the right information about the magnitude of the reactions of the 3 supports, and we're just going to add this to the figure. So I was about to write on the screen. All right, so it's right here. We have reaction at A equals reaction at C because of symmetry, and then reaction at B is 125 distributed load times L. L is, so in our case, L is going to be 1.6 meters. W, this is W, and then we have RA equals RC, and then RB. So 3WL over 8, 3WL over 8, and this makes for 3 times 50 times 1.6 over 8. So 3 times, we said 50 times 1.6 divided by L over 8 equals, so this is 30 kilonewtons. And this is likewise 30 kilonewtons. And then the middle support, it's 1.25 W. So 1.25 W times L. So that's 50 times 50, 1.5 times 50 times 1.6. This is 100 kilonewtons. Okay. We can look at this graph and repeat it for our problem. But once you know the reactions of supports, then essentially this is charted ground force, because you can assume this like being an external force that's added to the distributed load. Okay, so let's draw I'm no longer looking at the appendix. Let's draw the shear diagram. So we begin with I could move a little bit up. Actually, I could stay on just on this line here. So 30 W, or rather V, I'm sorry, in kilonewtons. So jump by 30 up, and then I have a distributed load that is even, and so that will cause V to decrease at a slope of 50 kilonewton per meters. I want to know what the magnitude of V is right before point B, where there will be a jump that is, diagram moves up by 100 kilonewtons. So I have 30, and I'm subtracting 50 times 1.6. So 30 minus 50 times 1.6, and this is negative 50. So I have negative 50 here, a bit more than negative 50. And again, it goes linear. And then the 100 jump, so this makes positive 50. And then I repeat the same slope, so I repeat a line that goes parallel, or yeah, they're parallel, same slope. And so I have plus 50, and so 50, and then negative the same area, 50 times 1.6. And this is negative 30. And of course, if when I move or right after point C where there's no load, this one intervenes and the diagram closes to 0. Okay? And I can draw the moment diagram. So the moment diagram, M, will be in kilonewton meters. And I'm expected to have, so I see 0 here. This is a smooth maximum or minimum. This is a likewise smooth. And here I have a flexion. It is tangent left and right are non-zero equal. So yeah, it's a cusp. Will look probably like this, or maybe inverted. Actually, looked inverted on the appendix. So let's see what how our values work get combined. So the x-axis, and since this is line, the moment diagram is a parabola. I'm starting with what? I start with a positive 30 kilonewton slope that goes to 0 and then continues and goes to 50. So there will be a max where the shear went to 0, yes. And we can find that. So I'll need to find what we'll call this A and B. I did this before, and we can use similar triangles. So I need to know what the max is. But again, the expectation is that the moment diagram will look like this. Okay, starts with a large slope, which goes to 0. Cannot be this way, because this is like the slope is increasing, okay? So this is the, and max is again at this point. So let's see what A and B are. We have firstly that A plus B is 1.6. And then from similar triangle, or you can write equation of line. So I can write 30 over 50 equals A over B. Okay? So let's explicit A is function of B. So A is going to be 1.6 negative B. So 1.6 negative B over B. So this is 1.6 over B minus 1. Or 30 over 50 plus 1 equals 1.6 over B. Okay, so 30 over 50 plus 1, that's 80 over 50. So this is 80 over 50. So B is going to be 50. So B is 50 times 1.6 over 80. All right, or could I say just 8 over 5? Why carry is unnecessary 0. Okay, so 5 times 1.6 over 8, and this is 1. B equals 1. So I have this equal 1, and it means that this one is going to be 0.6 meters. Okay, so now I can tell the moment here at point, could know the A, B, C, can call this D and E. So what is the moment, the bending moment at point D? Who wants to help? Okay, so you evaluate the area of this triangle. So it'll be 30 times 0.6 over 2. So it's 9. So I have 9 kilonewton units that we agreed upon. And then this goes to some value at point B. Let's see if it's remains positive or if it goes negative. In the appendix appeared to went below to have gone below the zero axis. So to get that to N9, we add a negative area or subtract 50. 50 times 1 divided by 2. So 9 minus 50 over 2, that is minus 25, and it's negative 16. So it goes to, smoothly, it goes to negative 16, I said. Okay. So yeah, and this is it. Because of symmetry, now I can just mirror the graph. I could continue, but this is the way it looks. All right. Same 9, and it goes to 0. So we've got the shear force bending moment diagrams. For, what does it say? Deflection. We also need to find, to get deflection. Yeah, we can do that. We still have it. Yeah. So let's see what information we have for deflection. The deflection, maximum deflection, it says, is at x1. So x1 would be some distance. So where, so x1 is where maximum deflection is, or maximum deflection. And because of symmetry, it's also likewise if you measure from the other end. So this is where y max is, x1 for y max. So I'm going to erase here, and we can evaluate that maximum deflection. We have the equation. So it would be negative w L at power 3. So y max is negative w times L at power 4 over 185 EI. EI. Okay. We don't have information about E and I, but we can leave this as any value could be substituted. So, and actually it even says put it in the form 1 over EI times. So it'll be negative 1 over EI. And then the rest would be 50. And then 50 is magnitude. So we have it 20 kilonewtons. Deflection is negative down. So 50 times 1.6 at power 4 over 185. So 50 is W times 1.6 at power 4 equals over 185 equals. So this is, yeah, I could put it on top. So 1.7712 over EI. And it happens, or is at x1 equals, it says from 8. So 0.4215 times L. So 1.6 times 0.4215. 4215 equals, that's 0.6744 meters for our problem. Was it clear? So straight from, it was a loading pattern. Actually, no, where I'm at. Need to bring this to where it matches my notation. Kind of. Maybe now. Okay, so if you're to take a photograph, this will be a good alignment between the problem statement or figure and our solution. Questions? Supposed to take a photograph. She missed a few minutes. Share the picture. I'll step away. I erased the simple analysis to find where the shear diagram goes to 0, and it's where the moment reaches these two positive maximums. So I just wrote similarity between these two triangles, and they also say that A plus B equals 1.6 for L. Okay. Let me erase the board. This problem was documented as statically indeterminate continuous beam, it's called, but could be, it might not be the best motivator, but could be analyzed as using principal superposition. So of two statically determinate cases. So it could be the case of, or we can analyze is the overlap between, let's see, between this case A and the, I don't think we have one that's without an overhang. No. So between A and D, ignoring the this part here, the section from C to D. So let's see if we can do it that way. You have a question?
Yeah, I do.
For the early problem.
You mentioned this term statically indeterminate. Logically, it sounds like it's stable, but we're like missing one or two variables.
Okay, so what does it mean? This is statics. So what does it mean it's statically indeterminate? Using statics only, you cannot solve for the reactions of the supports, okay? So our statically determinate case is a simply supported beam, like we did so many, and the cantilever, okay? So our two statically indeterminate cases are this one, all right, with some loading distributed, and then the other one is the cantilever, okay, with some load distributed, whatever. You can have a moment applied. So using equations from static, you can state in 2 dimensions 3 equations, equilibrium equations. Sum of forces, 2 sum of forces equation, sum of force in x equals 0, sum of forces in y equals 0, and a moment equation, sum of moment equation. Okay, so you can handle 3 unknowns. Now, here we have, it says load just from above. We have just vertical loads. So there will be 2 unknowns. Here we have a force and the moment. Here we have force and force. So really stating equilibrium equation, you can solve for the unknowns. But if I add, like for the cantilever, if I add a support here, a sliding support, then this comes in with an additional, so I have 1, 2, and the third unknown. And I cannot solve, or state equilibrium equations in sufficient number to solve for this. For the earlier problem that we did earlier, we had an additional support here. So we have 1, 2, 3 unknowns, and I cannot determine them using our classical way. But there's we can use formula method to figure out this kind of problems. So we can assume this to be an overlap of a statically determined beam that is loaded with with W. Okay. So I have reaction of the supports for this instance are a and let's say 1 RC1 equals, again, this is just W and it's 50 kilonewtons and L, all right? And then I can take the same beam and load it with a force from below that I don't know. I call it RB, such that, and these will be RA2, and this will be RC2. But I'm setting the condition. Let me show the distributed load is pointing down. That the deflected beam, so like right now, the deflected beam, just due to the distributed load, will be this. Under the effect of a force like this one, acted from below, I have this. Principal superposition says that, and so again, I could analyze the problem where I have a simply supported beam with distributed load and a given force acting in the middle, and I can get the resultant deflected shape of the beam by just adding, at given x, says I just add them one by one, if I'm to work numerically. If I have equation of this line and equation of this line, I just add them. Okay, so it will be y of x, y1 of x equation. This one will be y2 of x equation. The resultant equation will be y of x equals y1 of x plus y2 of x in general. So again, assuming this is given, I can analyze the two because they're documented. The back of the was the formula, and then I just, to get the resultant deflection, I just add them, and you can add them throughout, and you state the equation of the deflected beam or at the locations of interest. Well, I can also use this to say that, for this with carrying an unknown RB, I say that I, or rather y of x equal L equals 0. Does it make sense? So you start with this cantilever, it deflects, and you keep on increasing this force until you reduce this deflection at B to 0. Does it make sense? Is it clear what I'm explaining? Okay. So we can try this. The uniformly distributed load case is this one. Of course, we have L is the full length, not the just half length, but it says, and we're at the middle, so both cases maximum deflections at the middle. So it's a simplifying case. So y at B is 5, and just look here. They have this capital W notation. Capital W is lowercase w times L. So essentially is the equivalent, so total load W equals lowercase w. So would be I drew it was dashed line, if you remember. So this, the equivalent concentrated force to a distributed load. Okay, so for this, and so I'm at point B, and I write, where is it? Y at B is, it will be y at B1, the way we have it, is it's -5 times would be what? Lowercase w times, for our case, times 2L. All right. And 2L goes at power 4 over 384 EI. 384 E times, or it was E times I. Okay. And then for, I'm looking now above, so maximum deflection, again, they happen to be in alignment. So I know the maximum deflection is in the middle. It says at the center, and it's PL at power 3 over 48. If P is above, deflection is down. If P is it acts from below, deflection is up. So I need to flip the sign. So Y for this 2 case, again, this is case 1. This is case 2. So I have YB case 2 is going to be the plus version, what you see there, PL at power 3 over 48 EI. Our P is RB. And then, and again, negative term positive L is going to be 2L at power 3 over 48 EI. Okay? And I can also tell these right away. So I have RA1 is going to be essentially this. So it's going to be, I can put numbers, so it's going to be half of the equivalent concentrated force, so it'll be 50 times 2L over 2, so it's 50 times L, or 50, yeah, I could say W times, for our case, times L. And then likewise here I have lowercase times W, all right? As for here, this is going to be RB over 2. And this other one, it's going to be RB over 2. Does it make sense? Ultimately, this is going to be WL minus RB over 2. And saying this one, RB, well, we'll find it. And so this one is WL minus RB over 2. So what we need to do is to just say this plus this equals 0. And we'll solve for the unknown, which is RB. That makes the deflection at the middle, when I combine the two effects, 0. So this is how I got RB. Does it make sense? Again, you assume the statically determined case, and then you come in principle superior with a force from below, and you modulate, increase the unit until this deflection goes to 0. This is what we capture with these two equations. So I'm just going to say, YB1 plus YB2 equals 0. So this means that the two together equals 0, or this equals this. So it'll be 5 lowercase w times, what is 2 at power 4? 2 at power 4 is 32 at power 4 equals 16 times 16 times L at power 4 over 384 EI equals this other one with the unknown RB times 16 times L at power 3 over 48 EI. Okay, so what is RB from these two equations? Well, firstly, these come out, and I have an L at power 4. I have an L at power 3 here. This goes out with this one. 16 goes out. So RB is going to be 48 times 5 W, 48 times 5 times lowercase w, over 384. Okay? So let's see what this is equal to. We know what to, was it? I erased the board. So what was this? 1.25. What was this? 1.25. I need to go back to the appendix. So the statically undeterminate, and it was entry what? G. Yes, and RB 1.25 W times L. Lowercase w times L. So let's see if this is this value here. So 48 times 5 over 384 equals. It's 0.625. Have we missed anything? Maybe there's an L on one hand. So 48 times 5. Oh, okay. 48 times 5 over 384 W times L. Does not add up as I was expecting. Maybe we missed something. So one more time, I'm looking at, so I say PL at power 3 over 48 EI. PL and L is 2L. Oh, okay, so this is 2 at power 3. So the mistake is here. It's not 16, but rather 2 at power 3. And that's 8, okay? So I'm left with so with 16 here, 8. So the correct would have been 48 times 5 times 16 over 8. And now I think we're good. So 48 times 5 times 16 over 8 over 384. 384 equals 125. 1.25 W times L. Well, how about that? So on occasion we have it right. We'll get it right. As for these here, so let's see if I have for RA for the combined case, which is RC, I have W times L minus, and RB was 1.25 times W times L. So what is this equal to? Does it turn negative? RB, WL I said, so WL is this one, minus, oh, this is over, RB over 2, is that right? So I need to say over 2. Okay, so I'm saying 1 minus 1.25 over 2 equals, and this is 0.375 W times L. Okay, the actual case, statically indeterminate case, it listed as 3 over 8. Okay, so 3 over 8 is nothing but 0.375. All right, so do you understand what is this coming from? Principal superposition, it's called. And now we have reactions to supports. We have RB. We can draw the diagrams. Remember, all we use for the actual case documented, that is entry was a G. We use just this one was H. I see difference of notation. No, the same. I have the old edition with me because I don't want to put the 6th edition. But what we used from what was documented in the appendix were just the reactions at the supports in this and the middle support, and of course the equation of the the maximum deflection. All right. If you want, so I'm not done yet. If you want the equation of the entire beam, all you need to do is, like I said, to just take the case for distributed load, the case for a concentrated load, now that you know its magnitude 1.5 WL, and you state this, and you might have to write it piecewise. You oftentimes see between 4 x going between A and B, and then 4 x going between B and C, to have different forms. But otherwise, we could handle some of the cases, statically indeterminate cases, using principal superposition. Okay, let's look at, as this was projected earlier, let's look at your exam problem. So let me calculate deflection. What time is it? 1:46. So let's calculate deflection, maximum deflection for your test 3 problem, this problem 2, using principle of superposition. So you're well familiar with this. What would be the take? You know, how we're going to analyze this problem. And move it back here. And I take another screenshot. I'm sorry. So Alt, print screen, paste. Oh, a lot of figure. Actually, this can be made small. Undo. Okay, so we need to look at the back of the book and see how we can model this as individual simpler cases. And I don't like it. It's too big. So would be the overlap. Let me move this up, and I'm going to make my own drawing. This is a simple. So it'll be the overlap of distributed load case 1, the mirror case, another distributed load, and then a load in the middle, same as the one that we looked at earlier. All right, so it will be, like I said, I'm going to redraw a smaller figure. So distributed load was W on a simply supported beam plus another distributed load but mirrored. Okay. And then a third case on a simply supported beam, one load in the middle with P. So W, W, and P. Does it make sense? And let's say we want the equation of the distributed. So due to W alone, the beam will deflect probably something like this. And then it goes like this, just a mirror, and then this one. So for example, if I'm interested in the deflection at some distance x, I take this piece, I take this piece, and I take this piece with their sign. So it'll be y1, y2, and y3. And y of x would be y1 at x plus y2 at x plus y3 at x. Okay? So let's see what the appendix has to offer. We have the simple case distributed, or the concentrated force right in the middle, which will be this one. And actually, well, let me make this small to where we can see what's on the. Oh, went away. Right. So it says. Let's see how x is, and it's also our x. And what is L? So L is going to be on the figure. So L, we need to match notations. So that's L over 2. L over 2, and it's equal to 0.4 plus 0.15. That's 0.55 meters. Okay. And we can, so it says for x, I could say on this case, so y3 now of x is and I repeat this equation to A and B. So negative P times X over 48 EI. And then I have 3 L at power, was it 2? Minus 4 X squared. All right? And this is for X going between, would be 0 and L over 2. Let's look at this one. So I have y1 of x equals. So we need to go to where we have a, let's see, is this our case? Uniform distributed load. No, this is on overhang. It's not ours.
Could we use E and then just
I know it's one of the document. Okay, is this one, right?
yeah.
I have A, which is other than L over 2. So this is our case. So it says between A and B, and then between B and C. So this is already piecewise defined. So like piecewise or with a curve bracket, and we have A is 0.4 meters. Okay, so let's see, between A and B, that is where distributed load ends, that will be for X going between 0 and A. Okay, and that's going to be this equation, right? So negative W, let's see, L was full length. So W X over 24 EIL. And then I have A squared. And then there's 2L minus 2L minus A squared. And then I have negative 2AX squared. It's pretty messy. Again, this is the price to pay when you make up things. X squared. So yeah, as I was looking at the projector, saying, okay, we can look at this one, minus A, and then I have plus LX squared. I just repeated that equation over there, okay? So that's for X going between, we said, X going between 0 and A, which is with A less than, so A is less than L over 2. Okay. All right. Now, oh, by the way, what do you do if if A is greater than L? You can use principal superposition. Essentially, take a uniformly distributed load and subtract from below one that is less, which is documented, but not our concern now. And then it says between B and C. So between B and C, that will be this interval. So I need to essentially repeat or state this equation, negative W A squared, and then I have L minus X over 24 EIL. Okay, and then the rest for L X minus 2X squared minus A squared. All right, and this is for X going between A and L over 2. We care about the equation just up to L over 2. The other will be just a mirror of it. And then lastly, we have this one, which is the mirror of the above equation. So essentially what I need to do is to state this. So y2 of X is this equation going between, it says B and C, but in reverse. All right. Some of these figures introduce a a variable like a mirror x. So how do we mirror this equation? Essentially, we need to change the variable. So I want to have, what is this equal to? It's L minus x. Is that correct? So in order to state the equation for y, going from C to B, actually we'll go just up to the middle, I need to make a change of variable here. So I need to replace x with L minus x. So this goes negative WA L minus, and then I have minus L plus x over 24 EIL. Okay, and then I have 4L, and then it will be L minus x minus 2 L minus x squared minus A squared. I'll probably use, and this is for x, and likewise so for x going between 0 and L over 2. Okay? Well, you exchange your smile, so it's impossible to see this anytime, so why pay attention?
It's just math.
Well, I mean, you know, we choose to go to the moon and do other things not because they're easy, but because they're hard. So we have the three equations. Actually, yeah, three of which one is piecewise. You just put them together. And you can, if you have, for example, y max is just going to be, you know, I'm looking here. By the way, better this wise, that is piecewise continuous, better have the same value at A. So one of these should be excluding the limit. But if you make A, or like x equals A in any or these two equations, these should get the same value. If not, something's wrong. And the mistake, you know, cannot be but in the original equation. But if you want to y max, you just say y, you make, so it'll be for x equals L over 2. And that will be the case of, actually will be this equation where I make x L over 2. This equation that I make x equal L over 2. And this one that I make x L over 2. So yeah, it looks messy, but I've seen worse. Okay? Do you understand how principal superposition works? So whatever it's documented in the appendix, see if you can combine them to get your loading case, possibly with mirror, and of course with reversing the, so we can have, for example, cases where the distributed load has to act from below. So I said, if I have a case like this one, you know, I have a simply supported beam with a distributed load. I'm making, do you understand the difference between these two? This is a fixed end. This one allows sliding. So as the beam deflects, it tends to move. If I fix this end and this end, allow slow, the beam will help add strength by its own tension. All right? Zekker's program using finite elements can capture that, but not our analysis. Anyway, so if it passes the middle, then what do we do? Well, you can say this is being a distributed load, that it's full distributed load. Well, I said is, yeah, full distributed load plus a distributed load that is negative or from below. Actually, that makes a positive value. Does it make sense? So I have the fully distributed load. I subtract this. I get the case, or rather this one and this one are documented. This just being mirror. of what's available. So this one is for A less than L over 2. And I used it here, and this is a distributed load over the entire span of the beam, and it's documented. Okay? All right, we'll do some more, and then flexor muscles with successive integration for the cantilever cases. I mean, I'm telling you now that successive integration is useful when you might find this kind of tables with more information elsewhere. So if you have a triangular distributed load, okay, and I say cantilever, why? Because constants of integration are easy there. You know that deflection and slope are 0 at the very where x equals 0. Otherwise, you would have to. There are some graphical methods, and I mean, heck, I did a spreadsheet that can do any of the cases discussed in the book and others, in using the theory in the book. So when you have a taper load, and when you have, and I'm talking again cantilever, so when you have I that varies, so I have moment of inertia in different moment, 1 and 2. We did a problem where there are 2 pipes, one inside of each other, and you can even capture the if there's an overlap, say you have a few inches of overlap, and then you will have another section, so it will be I1, 2. Does it make sense? Pipe alone bigger, the 2 pipes together, the thinner pipe, I have 1, 2, 3, same material, although it could vary. I can have, the difficulty would be when the 2 go together, aluminum and steel. But otherwise, if I neglect the overlap, I can go with steel and aluminum, and I have I1 and I2. Problem is when they 2, you have a mix of, I don't know how to handle that. Okay, so this is when successive integration is useful. Not documented, and I changes along the beam. Thank you. Is 2:03. I haven't gone 10 minutes over the scheduled time. This was it for now. And